Hello, welcome. In this short video, let us look at the proof for Jensen's inequality in the case of convex functions. So Jensen's inequality states that for a function f, which is a convex function, the function of the sum I equal to 1 to m lambda I xi is always less than or equal to the weighted sum I equal to 1 to m lambda I f of xi. Here lambda I is always positive and the sum lambda I is equal to 1. So now we want to prove this theorem by using the principle of mathematical induction. So for m equal to 2, we can easily see that f of lambda 1 x1 plus lambda 2 x2 is less than or equal to lambda 1 f of x1 plus lambda 2 f of x2, which is nothing but the condition for a convex function. Hence the theorem is true for m equal to 2. So this is equation 1. And now we assume that the theorem is true for m equal to n. Our goal is to prove that it is also true for m equal to n plus 1. So for m equal to n, we have f of summation I equal to 1 to n lambda I xi is less than or equal to the summation I equal to 1 to n lambda I f of xi. So now put m equal to n plus 1 on the left hand side. So we get f of summation I equal to 1 to n plus 1 lambda I xi, which is equal to lambda n plus 1 x of n plus 1, of course f of, plus the summation I equal to 1 to n lambda I xi. So this one is equal to f of lambda n plus 1 x n plus 1 plus 1 minus lambda n plus 1 multiplied by summation I equal to 1 to n lambda I by 1 minus lambda n plus 1. Note that this is still a positive and we have xi here. Now if you look at this function, it just looks like the left hand side of the condition for a convex function. So this function is still less than or equal to the linear sum lambda n plus 1 f of xn plus 1 plus 1 minus lambda n plus 1 multiplied by f of the summation I equal to 1 to n lambda I by 1 minus lambda n plus 1 xi. But since lambda n plus 1 is independent of I equal to 1 or for all values of I equal to 1 to n, we can easily cancel these two factors. So this becomes lambda n plus 1 f of xn plus 1 plus the summation, the function of the summation I equal to 1 to n lambda I xi, which is nothing but the left hand side of this, that is inequality 2. So this, which basically implies that the right hand side is less than or equal to lambda m plus 1 f of xn plus 1 plus summation of I equal to 1 to n lambda I f of xi. And then if you look at this lambda I, and if you look at this summation, it is nothing but the linear sum I equal to 1 to n plus 1 lambda I f of xi. Therefore, when the theorem is true for m equal to n, we also have the proof for m equal to n plus 1, that is the summation I equal to 1 to n plus 1, the function of the summation lambda I xi is definitely less than or equal to the summation I equal to 1 to n plus 1 lambda I f of xi. So from this result we can say that since the theorem is true for m equal to 2 from equation 1, since it is true for m equal to 2, and from this result we can say that it is also true for 3, 4, 5 and so on. So hence by mathematical induction induction, we can say that Jensen's inequality I equal to 1 to m, function of I equal to 1 to m, the summation I equal to 1 to m lambda I xi is definitely less than the summation I equal to 1 to m lambda I f of xi. Given lambda I, the summation of lambda I is equal to 1. Thanks for watching.